axes of an aircraft will be covered more in depth in the flight controls chapter. However, it is important to know the 3 axes that an airplane can move on. The first is pitch. The pitch, or lateral axis, is the point that a plane will pitch its nose up or down on. The roll, or longitudinal axis of an aircraft, is the point where the airplane will roll to the left or right. And the yaw, or vertical axis, is the axis that the plane will yaw on or move its nose left and right. It is also important to note that each of these lines runs through the airplane's center of gravity. Each aircraft responds to control inputs differently and therefore handles differently. For example, a smaller aircraft might respond rapidly to control inputs, while a large transport aircraft may feel sluggish and slow to respond to inputs. These features can be designed into an aircraft to facilitate the particular purpose of the aircraft by considering certain stability and maneuvering requirements. There are 2 types of stability: static and dynamic. Static stability refers to the initial tendency or direction of movement back to equilibrium. In aviation, it refers to the aircraft's initial response when disturbed from a given angle of attack, slip, or bank. Positive static stability is the initial tendency of the aircraft to return to the original state of equilibrium after being disturbed. Neutral static stability is the initial tendency of the aircraft to remain in a new condition after its equilibrium has been disturbed. Negative static stability is the initial tendency of the aircraft to continue away from the original state of equilibrium after being disturbed. Dynamic stability refers to the aircraft response over time when disturbed from a given angle of attack, slip, or bank. This type of stability also has 3 subtypes: positive dynamic stability, neutral dynamic stability, and negative dynamic stability. These act in the same way as the static subtypes, but these subtypes explain the same relation over time as shown on the above graph. Stability in an aircraft affects 2 areas significantly: movement and controllability. In designing an aircraft, a great deal of effort is spent in developing the desired degree of stability around all 3 axes. But longitudinal stability about the lateral axis is considered to be the most affected by certain variables in various flight conditions. Longitudinal stability is the quality that makes an aircraft stable about its lateral axis. An aircraft with an unstable longitudinal axis will have a tendency to dive or climb and can become unsafe to fly. Static longitudinal stability or instability in an aircraft is dependent upon 3 factors: location of the wing with respect to the center of gravity, location of the horizontal tail surfaces with respect to the center of gravity, and the area or size of the tail surfaces. The above picture shows these forces balanced in flight. The center of lift in most asymmetrical airfoils has a tendency to change its fore and aft positions with a change in the angle of attack. The change in lift tends to move forward with an increase in angle of attack and to move aft with a decrease in angle of attack. This means that when the angle of attack of an airfoil is increased, the center of lift, by moving forward, tends to lift the leading edge of the wing still more. This tendency gives the wing an inherent quality of instability. Most aircraft are designed with a nose heavy or a center of gravity that is in front of the center of lift. Even when the horizontal stabilizer is level during flight, downwash from the wings pushes the horizontal stabilizer down. Generally, the manufacturer of the aircraft will give the horizontal stabilizer an angle that will provide the most stability during flight at a given speed and power setting, as shown above. For a nose-heavy plane, when the airspeed is slow and there is less downwash on the tail, the nose will pitch over more aggressively. Thrust can also affect the longitudinal stability of an aircraft. Reduced power causes less downwash, and causes the nose of a nose-heavy airplane to naturally pitch down, which is a desirable characteristic in an aircraft in order to make stall recovery easier. Stability about the aircraft's longitudinal axis, which extends from the nose of the aircraft to its tail, is called lateral stability. There are four main design factors that make an aircraft laterally stable: dihedral, sweep back, keel effect, and weight distribution. A dihedral design is when the wings are connected to the fuselage a few degrees higher than from being perpendicular. Therefore, when the aircraft is viewed straight on, the wings point slightly upward like a V. The angle of attack stays high if one wing is lowered and will attempt to lift back to its stable position. If the other wing is lowered in the process, it will then be lower and raise up until the oscillations subside. In addition to a dihedral design, aircraft may also have wings that are swept back. This design allows the lower wing's leading edge to hit perpendicular to the relative wind. This causes greater lifting effect, and the wing restores to its original position. An aircraft always has the tendency to turn the longitudinal axis of the aircraft into the relative wind. This weather vane tendency is similar to the keel of a ship and exerts a steadying influence on the aircraft laterally about the longitudinal axis. When the wing dips, the weight of the lower half of the plane acts as a pendulum to steady the aircraft. This effect is called the keel effect, and its effectiveness can be changed by weight distribution to make more of the aircraft under the center of gravity. Stability about the aircraft's vertical axis, the sideways moment, is called yawing, or directional stability. Yawing, or directional stability, is the most easily achieved stability in aircraft design because the vertical fin and the fuselage aft of the center of gravity are the main contributing parts that cause the aircraft to weather vane or point its nose into the wind. If the area of the fuselage aft of the center of gravity is larger than in front of the center of gravity, the aircraft will be vertically stable. Also, to add to the stability, a vertical fin is added much like the feather on an arrow. The fin being placed on the tail helps keep the wind from yawing the aircraft to the left or right. Free directional oscillations, or Dutch roll, is the tendency of the aircraft to yaw and roll in a figure-8 formation. However, most aircraft are built with spiral instability instead. This instability causes the plane to yaw in one direction, and if not corrected, the aircraft will enter a deep spiral dive. However, this tendency is usually easily controlled by the pilot. An aircraft is not turned like a car or a boat. To turn, the aircraft must be banked. When the aircraft is banked, the lift acting does not act straight up and down. In a turn, the lift component is broken up into a vertical and horizontal component. The horizontal component is the force that is involved with turning the plane to either side. If the lift and weight continued to act straight up and down in a bank, the plane would remain pointed in the same direction. The rudder is used to correct any deviation between the straight track of the nose and tail of the aircraft. A good turn is one in which the nose and tail of the aircraft track along the same path. If no rudder is used in a turn, the nose of the aircraft yaws to the outside of the turn. The rudder is used to bring the nose back in line with the relative wind. The important thing to consider is that the horizontal lift component, not the rudder, is used to turn the plane. During a turn, the aircraft loses some of its vertical lift, which requires back pressure on the elevator to maintain a consistent angle of attack. Also during a turn, the increased drag causes the airplane to lose airspeed. If a constant speed, constant rate turn is required, then additional power may be needed. An aircraft is balanced whether it is in straight and level flight or in a climb. However, to transition from straight and level to a climb, there must be back elevator pressure applied. When this happens, the wings have an increased angle of attack and momentarily generate more lift. If no power was added for the climb, the airspeed would gradually diminish because the thrust required for a climb is greater than the thrust required for level flight. An aircraft is able to climb at a certain airspeed only because of excess thrust. When this thrust is gone, the aircraft will no longer be able to climb and will start to lose airspeed. This same principle is applicable to descents. During a descent, elevator pressure is applied forward, which causes the wings to momentarily have less lift. This causes the nose to drop, and the airplane will start to descend. This time, the power must be reduced to maintain a constant airspeed. When an aircraft rapidly loses lift on its wings, a stall occurs because the critical angle of attack for the airfoil has been reached. Stalls are one of the most misunderstood areas of aerodynamics because pilots often believe an airfoil stops producing lift when it stalls. In a stall, the wing does not totally stop producing lift. Rather, it cannot generate adequate lift to sustain level flight. Most aircraft are designed to stall from the wing root out to the wing tip. This provides the ailerons to have some authority during a stall. The stalling speed of a particular aircraft is not a fixed value for all flight situations. But a given aircraft always stalls at the same angle of attack regardless of airspeed, weight, load factor, or density altitude. A stall can happen at low or high speeds and during turns, not just when the aircraft is flying slowly. In the picture above, the pilot is traveling at 100 knots, but pulls back on the elevator sharply. The result is that because gravity and centrifugal force prevent the aircraft from immediately changing directions, so the angle of attack is increased from low to very high, and the aircraft could stall. When centrifugal forces are added, such as in a turn, the stall speed increases. Most training aircraft are built with the center of gravity in front of the center of lift. This means that during a stall, the aircraft will rotate about its center of gravity and nose down. This condition is better than having the center of gravity behind the center of lift, because if the nose cannot pitch down during a stall, the aircraft will remain in a stalled state until it contacts the ground. If ice is allowed to accumulate on the aircraft during flight, the weight of the aircraft is increased, while the ability to generate lift is decreased. As little as 0.8 millimeters of ice on the upper wing surface increases drag and reduces aircraft lift by 25%. Pilots can encounter icing in any season, anywhere in the country, at altitudes of up to 18,000 feet and sometimes higher. The aircraft propeller consists of 2 or more blades and a central hub to which the blades are attached. Each blade of an aircraft propeller is essentially a rotating wing. As a result of their construction, the propeller blades are like airfoils and produce forces that create the thrust to pull or push the aircraft through the air. A cross-section of the blade shows that the top surface has a camber much like the top of the wing, and the bottom is flat, much like the bottom of a wing. The chord line in a propeller is the line drawn from the leading edge to the trailing edge. On a propeller, the thicker end is the leading edge. As shown above, each section of a propeller blade moves downward and forward. The angle that the propeller strikes the relative wind is its angle of attack, which produces thrust. Also, this blade's camber acts just like a wing to create forward lift. The pitch, or blade angle, says how much of a bite the propeller has or how much air it handles in one rotation. On most smaller aircraft, the pitch or blade angle is set and cannot be changed. But in larger aircraft, the pilot may change this to adjust the load on the propeller and to control engine RPM. These propeller systems are called constant-speed propellers. Propeller efficiency can range anywhere from 50 to 87%, depending on how much it slips. Propeller slip is the difference between the geometric pitch of the propeller and its effective pitch. The difference is geometric pitch refers to the theoretical distance a blade should travel through the air, and the effective pitch is the amount the blade actually travels. If the effective pitch is in a shorter amount of time than the geometric pitch, the propeller travels through the air too quickly, and that is referred to as a slip. The reason a propeller is twisted is to ensure that when the blade is spinning, the angle of attack of the blade to the air stays the same. If the blade were not twisted, for example, the part of the blade near the hub would be traveling slower than the part of the blade near the tip. This causes the part of the blade near the hub to potentially have a negative angle of attack, and the part near the tip to have a high angle of attack and be stalled during cruise. Therefore, to maximize the efficiency of the blade is twisted. To the pilot, torque, or the left turning tendency of the airplane, is made up of 4 elements which cause or produce a twisting or rotating motion around at least one of the airplane's 3 axes. These 4 elements are torque reaction from engine and propeller, corkscrewing effect of the slipstream, gyroscopic action of the propeller, and asymmetrical loading of the propeller, or P-factor. Torque reaction causes the aircraft to roll because the engine components are moving in one direction, so according to Newton's third law of physics, on the airplane above, there must be an equal and opposite reaction. Most newer aircraft are built with their engines offset to counteract this tendency. When the airplane is on the ground, this roll tendency is translated to the vertical axis and causes yaw. During takeoff, this yaw tendency is canceled by the pilot's use of rudder. Because of the high-speed rotation of the blade, the slipstream ends up being a corkscrew, which yaws the aircraft about its vertical axis. The more compact the spiral, the more predominant the force. However, as speed increases, the corkscrew elongates and becomes less effective. When airborne, this effect also causes the aircraft to roll on its longitudinal axis. The rolling moment caused by the corkscrew flow of the slipstream is to the right, while the rolling moment caused by the torque reaction is to the left. These forces would seem to cancel each other out, but they vary greatly, and it is the pilot's responsibility to control each tendency, regardless of which is more prominent. To understand gyroscopic action, you must first understand how gyroscopes respond to forces. The picture on the top shows a force being applied to a gyroscope. From the force acting upwards on the gyroscope, it should be noted that the response is yaw instead of the expected pitching motion. This is because when a gyroscope is spinning, the resultant force always takes place 90 degrees in the direction the gyroscope is spinning. In an aircraft, we can simulate that same force by pitching the nose up and down. The applied force is from the tail of the aircraft, and the resulting force takes effect 90 degrees in the direction the propeller is spinning, in this case counterclockwise from the pilot's view, and therefore the plane would yaw to the right. The pilot must control this motion with proper use of the elevator and the rudder. When an aircraft is flying at a high angle of attack, the blade of the propeller moving downward has a bigger bite than the blade moving upward. This causes the center of thrust to be moved to the right side of the prop disc area, which causes a yawing movement toward the left. The reason is that the blade moving downward has a greater speed through the air because it's moving into the wind, while the blade moving up travels with the wind. Because the propeller is an airfoil, the faster the blade moves through the air, the more lift it produces. Therefore, the faster moving blade causes an unbalanced forward thrust, called P-factor, or the asymmetrical loading of the propeller. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.